Hello everyone once again. I have switched into English because the talk will be in English. And here's our last talk at the summer school. And I'm happy to introduce Denis Yarats, who is a researcher at Facebook AI Research and also a PhD student in the University of New York. Denis has previously worked in different well-known research and development companies. And his research interests includes reinforcement learning and dialogue systems and text generation. And now Denis is going to tell us about the text generation in goal-oriented dialogues. Let's greet our speaker.
Thank you. All right. I guess, yeah, first of all, I want to apologize because you probably want to watch soccer right now, and you have to watch my boring talk. But so yeah, today I'm going to talk about. I guess I don't know. Okay, then I guess you don't want to. The joke didn't work. Okay. Right. So yeah, today I'm going to talk about the work that I did last year. It's going to be presented next week at ICML. So, and I guess today it's kind of like, so I guess I mostly work on reinforcement learning, and last year I tried to apply reinforcement learning to dialogues, and in particular to one interesting problem. So, one second. Should I point it somewhere, or? Okay, now this works. Yeah, so I guess first I'm going to introduce, maybe not a lot of people know what is Facebook AI Research. So this is a research lab that mostly work in kind of areas of AI. We have a lot of different directions: NLP, vision, reinforcement learning. Now we're going to have robotics lab, and we have many locations. I guess main location is New York City, and then the biggest, I would say, and then Menlo Park is pretty big one. So I'm currently in Menlo Park, but I'm for summer, but then I'm going to move back to New York. Right. So yeah, so today we're going to talk about the kind of like goal-oriented dialogues. In particular, I'm going to describe the problem of negotiation. This is, I guess, one kind of a problem of dialogues. Sorry. And the overview is going to be, I'm going to introduce the kind of the problem itself. I'm going to talk a little bit about the data set and what we're trying to solve. Then I'm going to tell you a little bit about the baseline model. It's kind of like what the simplest approach we can create to just like verify that everything is working. And then we're going to discuss the issues with this approach, why it doesn't work, and what we can do to solve it. And then I'm actually going to move and discuss the paper. And then we're going to talk a little bit about the results of the work. So first of all, I'm going to kind of like define what is negotiation problem and why is it important to study. So negotiation is kind of very interesting problem by itself because it has two aspects. One is linguistics quality, so you need to train your agents to communicate in human language. And also, agents should be able to kind of like plan. They should know like some strategic aspects of the game because it's kind of, you know, not only you have to speak well, but you also want to plan ahead and like achieve your goals. So that's kind of interesting problem by itself. Right. So also, the thing is with negotiation is kind of the solution might be very hard to achieve because there could be several solutions. But one interesting thing about negotiation is it's very easy to verify how well you did at the end. So for example, imagine when you For example, you want to buy something, you want to buy a car, and then you go to a dealership and you start talking to somebody, and then the final price that you're going to pay for the car is going to be a result of your negotiation. So if you did well, you're probably going to pay less. If you didn't do well, you probably have to pay extra money. So, and I guess if you think about it, negotiation can be used in various ways. So we can apply it. It's kind of has these two sides. From one side, it's adversarial, because you kind of like, you want to get to a better solution for yourself. You're going to achieve some goal, but also you have to be you have to cooperate with your opponent, because otherwise, if you're just going to be saying I'm going to go with this price and I'm not going to change it, you're basically just like not going to agree, and then you're going to get zero reward. So I guess previously this problem wasn't really studied, and that's why we have to kind of like create our own framework and collect a data set. So we decided to go with the following approach. So we're going to have two agents, and each of the agents is going to get some goal. So that's what they want to achieve by the end of the conversation. The important part is you don't get to see other opponents' goals. So this information is hidden. Otherwise, it's kind of like different problem if you show this information. So then, given this goal, two agents start to communicate to each other. So that's going to be dialogue. And then, at the end of the dialogue, each of the agents is going to produce some output. So essentially, in our example with the car, the output is going to be price, right? And then if both of them agrees, I guess they're going to get some reward. If they don't agree, they're not going to get reward. And the goal of the agents is to maximize the reward, right? So here you can see that we need to do well in communication, so especially like if you replace one of the agent with human, right? If your agent is not going to talk well, then I guess you're not going to get to any goal, because you just like the human is not going to understand. Right. So one particular example of this, this is kind of like abstract framework. One particular example that we collected data for was a kind of simple task. It's called object division task. So essentially, you have three types of objects: heads, books, and balls, right? Each of the object, and I guess the set of the object is the same, right? So you can see this information is open to everybody. But then the hidden information is actually going to be values for each object. So and they're going to be different for each agent, right? So for example, for this agent, each book costs just like 1 point, which is probably not very important object, right? But the ball costs 5 points. So if they're going to negotiate, and obviously the goal is to maximize number of points that you're going to get at the very end of dialogue. So what you can do, you can start like talking to each other and then decide how you're going to split the objects, right? And the goal is to maximize number of points, but also if you're not going to cooperate, you're just like not going to agree, and then you're going to get 0 points at the end. So that's not very good. So you have to have an agent that communicates well and also tries to be smart about how they like negotiate and what kind of deal they're going to get. So what we did, we basically using this framework, we collected a lot of dialogues. So we basically asked the humans to play this game and communicate. And we did like, we provided like several restrictions. So the dialogues, so this is one of the examples of the dialogue that we collected. So as you can see, it looks like pretty complicated. So it's not that simple. There could be like several, it's not just like one proposal and then just like the other agent agrees right away. Sometimes they can be very complicated. Yeah, by the way, if you have any questions, feel free to interrupt me and ask. So we collected about 6,000 of the dialogues. We have, let's see, that we have like on average about 7 turns. So that's kind of like 7 sentences in a dialogue. And then agreement rate is 80%. So humans very good at agreeing each other, right? So because the task is not very complicated for a human, but it's still, so that's why they do like very well. And average score is 6. And we also computed the Pareto optimality metric, which is basically means it's just like, can you get a better deal for yourself without decreasing number of points for your opponent? And that's actually like pretty good, 76%. All right. So now I guess we're going to talk about, so that's data set introduction. Now we're going to talk about the model. So model is kind of like tricky because you have to do sort of like at least several actions. You have to understand what are you being told. You have to kind of like generate the language also to explain what you want to get, and also you have.
Can you tell me once more what was the input data? I mean, I understand it's Thomas playing, but what kind of was it? So
Yeah. So basic.
How many steps were?
Yeah. Yeah.
What the data?
Yeah. So basically, the data was these inputs. So we basically just like saying, so you get in like 2 books, or 3 hats and 1 ball, and you have to we like describe the task, and you have to like talk to, that was done in Mechanical Turk, so you have a chat, so you talk to other person, and you've been asked to kind of like get as many points as possible. So the humans, like Mechanical Turker, it actually sees this information only. And once they output, like, press the button that they think they agree on the deal, they're going to like output something like that. And we collect all of this data.
And what was given to the machine?
To the machine, so now it's basically we have this, we have the dialogue, and we have the outputs.
Dialogue just as is.
Yeah, just plain text.
Do the agents know how many objects another agent has?
Yeah, so the objects is the same. Yeah, it's just like the only information is hidden is values. Yeah. So that's why they know that there, in this particular dialogue there is only like 2 books, 3 hats, and 1 ball, and they have to divide it. Mm-hmm.
Does the agent know points for his objects?
Yes. Yeah. That's why he knows, for example, here it's just like I better get a ball because it's 5 points. So that's why. Sometimes I guess it can happen because like we usually randomly generate this data. Sometimes it can happen. It's just like naturally very easy divisible, right? Divisible. But sometimes it can be, just like one object is valuable for both of them. All right. So yeah, so I guess usually when you get in like new data set, you don't know much about it. It makes sense to go with the simplest model, and just you can use it later to just like verify. I guess if you have any problems with the data set, what kind of results you can get, and then you can later use this model as a baseline to just like see how you can improve this later. So the simplest model would be kind of like end-to-end approach. You essentially are going to have like some simple encoder, just like MLP network. You can encode the inputs. So, and we're going to have just one model, kind of just like LSTM, recurrent neural network, that's going to model. See, here, the dialogue, we kind of like flattening it, just like as a one sentence, and we have like, at the very end of each sentence, we have like some special token, just like this sentence ends, and then next turn, and so forth, right? So that's why it's kind of like very simple language modeling task. You kind of like have one sentence, and then you just read it through. And it also learns to output this end tokens. So that's why you know that now it's different agent is speaking. And then at the very end, so we have a kind of like action classifier that outputs softmax distribution over all possible selections, right? So because you have like a finite number of possible combinations, you can just like have softmax over them. And this classifier is actually being applied not on the internal states of the network, but on the text itself. So it's actually has also inside it has a recurrent neural network. We do this because it's kind of, we're going to reuse this action classifier later for each model. It's kind of like action tracking for dialogue, because you want to have it the same for each, for different models, right? Because you have to judge on how well your dialogue was, not on some other state, right? Because otherwise your network can cheat. And just like it doesn't care about the language, especially when you're going to do self-play. Agents, like, they don't need to produce very good language. I'm actually going to show examples later. They can just like communicate through some internal representation, and then you just get very high reward, but output garbage language. So that was important.
Yeah, you know that after these results were like made public about these game negotiations,
Yeah.
in media.
Yeah, I'm actually gonna show. Yeah.
I had a lot of calls here in Russia asking artificial intelligence. They invented their own language, so they will kill us.
Yeah.
Other garbage.
I've got email from some United States, like Air Force, something. It's just pretty funny. Yeah, it was pretty stupid. Anyways, okay, yeah, there is this, because this is the simplest model. There are obviously like some problems with this, and some of the problems like very, I guess, expectable. Mm-hmm. Yeah, no worries.
So with this model,
is it okay? Or it works. Okay. So in my understanding, what's going on here is not like very much like humans are doing negotiations. So when I'm trying to talk with somebody and split some values, what I'm trying to understand is how much it's acceptable for the other person. So I'm getting maximum. But in this way, what the machine tries to understand in the maximum is the maximum amount he can talk to another. So it's constrained not by the value, but rather with the amount of dialogue it can take. So
Yes.
It works.
Yeah. So yeah, I'm gonna talk about this. Yeah. This one, because we train it on just the data set that we have, and we use like maximum likelihood metric. So it's just gonna replicate whatever data set you have. It's just gonna follow the same distribution. So it's not gonna actually like invent like new strategies to negotiate. So it's just gonna capture whatever it's saw in the data set. And to change that, so that's actually this point. It cannot go beyond the strategies that it saw in the data set. And we don't want that because, and to fix this, we would use reinforcement learning on top. So what happens, you kind of like, initially you have your model, you teach the model to generate language, human-like language. And then after that, you're gonna have these two agents, and you put them into self-play game. And you're gonna use reinforcement learning to actually maximize the score. So now they're gonna actually care about doing something differently, because if they just don't, if you just don't update parameters and stick with the same model, it's just gonna be whatever you saw in the data set. Now you're kind of like gonna change the model by itself, following, I guess your objective gonna be is just how to maximize the score, and it's gonna be different. So it's gonna learn some new strategies. But yeah, there is obviously a problem with this, because now the objective is a reward, not language. So if you're not careful, the model is going to forget language very quickly because it's just going to diverge. And that's why you have to like train it carefully. You have to, I guess, we tried a bunch of things, but I guess what worked was you train was very, first of all, like very small learning rate with reinforcement learning, and then once in a while you would like run few updates for supervised learning, so kind of like put model back into the good parameters, so the language doesn't is not garbage. Yeah. So, but yeah, there is still issues with this model. So usually what happens, the model actually doesn't understand the semantics. It just like learns word similarity. So for human, it's very easy to see that let's see, for example, for this input, the first message and the last message, the output is the same. Actually, no, sorry. I guess let's start. First and second message is just words similarity is the same except the first word, but the meaning is very different, right? In this case, you're getting 2 hats and 2 books, but in this case, you're just getting 1 ball, right? So even though the sentence is the same, the outcome is very different. While if you do this sentence, it's actually the same, the second one. It gets the same output, but the language structure is completely different. So unfortunately, the baseline model, it doesn't learn this thing. So and because of that, it's just like performance of your reinforcement learning, and in general, performance is not as good as you want. Also, when you want to apply like reinforcement learning, I guess we used just like simple methods like policy gradient reinforce. The problem here is just the action space is very huge. So essentially, like each action is the next word, right? So at each timestamp, you have to output next word, right? And that's very complicated. And also, the horizon is very long because horizon is essentially just like how many, like in each sentence you have many words, and then you have many sentences in a dialogue. So that's kind of very the search space for your reinforcement learning is very wide. So the search tree, and that's why it doesn't very work well. It's just gonna find some suboptimal trajectories and optimize them. So that's why we want to change that. And also one thing that we used to improve performance was sort of like rollouts. I guess the idea is very similar to AlphaGo when they have kind of this like Monte Carlo pre-search stuff. So essentially the way it works, if you remember, we have a model that kind of like learns the entire dialogue and it knows how to switch the turns. So what we can do, we can use from one point, for example, we have this sentence and we want to kind of like model the rest of the dialogue. So what we do, we would sample your own sentences and the sentences of your opponent, and we are going to estimate score, and we do it like many times, so we have many samples, and then we just like choose whatever is the best. So that's actually works pretty well, and it kind of like improves the score. But it doesn't work super good because usually there is not enough diversity in your sample. So in this particular case, it would just like say kind of like maybe different words, but the meaning is the same, and then action classifier is going to produce the same amount of points. So even though this is kind of like form is different, but the meaning is the same. So I guess essentially the problem is just like these models, they care about they don't understand the meaning. They just like see the surface of your language, and that's not very good. And that's, I guess, the problem that I was talking about already. If you apply too much of kind of like reinforcement learning, you're going to get some crappy language. And that's, I guess, what we discussed before leads to this like news that Facebook had to shut down AIs that learn like some language. It was like last summer. Okay, so now I guess how we can solve all of these problems. So the idea is just because we didn't know how to learn we couldn't learn the meaning of the dialogue. So now let's just like help model and kind of like model the meaning separately. So let's just, instead of having this like one model end-to-end approach, we can split our model into two models. One model is going to be responsible for kind of like planning, and it basically just going to think what to say, kind of like plan ahead, and it's going to be responsible for your intent, and it's going to understand the meaning, and then it's going to communicate these signals to your language model, and language model is going to be responsible how to describe this meaning, right? So essentially, if I want to get the ball, I maybe just give it some signal that I want to get the ball, and then it's just going to generate language accordingly to the strategy. Okay, so yeah, it sounds, I guess, easy, but how we actually do this. So we're going to kind of like, let's roadmap. This model is actually not end-to-end. It consists of 3 models. So it's kind of like a little bit complicated, but at least it works. So first of all, we're going to just try action classifier. I already touched a little bit on that. Then we're going to just talk about discrete latent variables. So actually, this latent variables is going to encode the meaning, the strategies, and we're going to use them to communicate strategies to our conditional language model. And then I'm going to show you the full model. All right. So yeah, first of all, I guess very quickly, so that's the action classifier I talked about initially. What it does is essentially just like reads the entire dialogue, and it produces the softmax distribution over all possible actions, right? So we kind of like train it once, and we keep it. We don't change it. And then we're going to use it later for each model that we're going to have. And it's kind of like we're never going to change parameters of this model, so comparison is going to be fair. Also, another advantage of this, I guess we call it kind of like state tracker, is just here you can feed not the entire dialogue, but you can also feed like some prefix of the dialogue, maybe 3 sentences. And because the way we trained it, it's kind of can predict what, at this point, if the dialogue stops at this point, what's going to happen, right? So that's going to be important later when we want to predict the future of the dialogue. So I'm going to talk about this. I guess actions are the same for both agents because the number of objects the same, right? So yeah, usually I guess you can predict for 2 of them, but usually they should be like compatible, right? Because I guess we restrict the task is just like you take all the objects, right? And because of that, if you take some object, the rest goes to another agent, right?
So to make it clear, how you end the game if 2 agents generate actions which are compatible. So it's like
yes. So the game is over. Yeah.
Compatible relations.
Yeah. Yeah.
But if they generate incompatible actions.
That means they don't agree and they get 0 reward.
Okay, but how do you track that they generate actions? You can generate your proposal and can do times. So
Right. Yeah. So I guess right. So I guess they have to generate the token that basically means last. Right. And then I guess the way you can use it, if you have some prefix of the dialog, you just add this token, and then you apply the classifier on top of that, and it kind of like imitates the dialog. Yeah. All right. So now I guess the first step is just like, okay, so we have this hierarchical RNN. Essentially, just it's going to be like this. So you're going to have encoder. Encoder is just going to input the beginning of the dialog, basically at what the prefix of the dialog at the point where you stay right now. And then you're going to have this decoder just going to output kind of like the next sentence. So this is just going to be some, we use GRU, but you can use any, like LSTM works fine too. And that's going to generate the next message from another agent. And then you're going to read it and send it back. So that's how we encode the actions. So actually, this one doesn't really work because if you think about it, just like makes kind of like 2 layers of LSTM. And if you use like continuous representation to feed into a decoder, so that's actually pretty much the same model, just like more parameters. And yeah, so we have to change that. And the way we're going to change this, we're actually going to introduce kind of like this discrete bottleneck. So instead of us here communicating through continuous representations, we're going to communicate through discrete representations. So that's going to be essentially what to say model is going to generate distribution over all possible discrete actions. And then it's going to feed this discrete action to language model. And then language model understands this action and generate language. So essentially, if you here, you kind of like, your model is generated the probability distribution over words. You essentially like factorize your distribution into 2 distributions. One is the what to say model. Essentially, it's going to generate distribution over these discrete latent variables. And then you're going to condition your language model on these discrete latent variables. And then it's going to generate the language. Important part is just this model doesn't get to see the input sentences. So all communication happens through the latent variables. Okay, so now what we need to do from what we need to have from these latent variables is to kind of like learn representation for each of them, and these representations should encode the meaning of this particular variable. There is several ways to do that. There has been some work where people kind of learn to maximize likelihood of the next message. This kind of works, but it doesn't really work because what it learns is just Z now represents the similar strings, because essentially when you maximize likelihood of the next message, it's just like it kind of like should encode all the information about the form of the word. So what we did is just kind of like very simple addition, but it actually makes big difference, is instead of like optimizing likelihood of the next message, we optimize likelihood of the rest of the dialogue and actions. So essentially, Z now encodes kind of like your intent. So if you take this action, how it's going to affect the rest of the dialogue. Right. And that's obviously because you have to now encode more information. It's much harder to do. That's where action classifier comes to play. So essentially, when we maximize likelihood of the rest of the dialogue, what we can do to simplify it. Obviously, I mean, we can do it. We kind of can generate the dialogue, the entire trajectory, and maximize it. But we have to run many samples, and that's going to be very inefficient. So instead, we're maximizing the likelihood of the next message, and also using the action classifier that I talk about. We kind of it tells us how the dialogue is going to end. And we have these 2 losses, and we're going to maximize them. What it gives to us is actually like comparison with this method. Now, these latent variables, they're going to encode different meanings. So in the first case, if you maximize likelihood of the next message, what's going to happen is just like Z1 here, it's going to encode the same form, but not the same meaning, right? So that's the example we already saw. So it basically just like it doesn't do anything. While here, if we learn latent variables in a way that it's going to maximize the likelihood of the rest of the dialogue, it's actually now this Z2 represents the meaning, right, of this sentence rather than the form. So, and that's actually very important, and it's going to help model to perform better. Yeah, so essentially how we're going to do that, we're going to use, it's kind of like now this problem is very simple to, very similar to clustering, so we can use like EM algorithm. You kind of, what you can do, you have this like discrete bottleneck, so it can take any actions, and then what you're going to maximize is the next message, and using action classifier, you're going to predict how the dialogue is going to end. And we call this clustering model. And using this model, you can just use kind of like the expectation maximization algorithm. So you're going to like, the forward pass would be for each latent variable you estimate your likelihood, and then you take the one that gives you the highest likelihood and you backprop it. So it's kind of like, it basically, instead of one forward pass, you do number of forward passes equals to number of clusters that you want to have. So usually, I guess you can do like 50. I guess in this work we have like maybe 200 or something like that. But you still have to do one backward pass. So usually forward pass is much cheaper. So that's, and you can batch it. So you can kind of like, it basically your batch size increases by this constant. So it actually works pretty fast. And then, yeah, I guess what we minimize, this loss, this is likelihood of the next message. And here, we just minimize scale divergence between the probability distribution that action classifiers predict and the probability distribution what our model is going to predict. So essentially, just if it converges, that means it's just our discrete latent variable is going to represent the meaning of, or whatever, like how the dialogue is going to end. Okay, so now we have these latent variables. Now we need to train language model that's going to take latent variable and generate kind of like, it's going to describe this latent variable, right? It's going to generate language that corresponds to this latent variable. So for this, to do that, that basically means it's just, your model should be very, it should be very accurate to, it's kind of like it should decode the meaning of your latent variable. So if this thing is kind of like encoder, it's like encoder bottleneck, and then you have to, with your language model, you kind of have to decode. And that's why, to do that, we do the following trick. Instead of just like feeding, this is actually important, so I'll try to explain to my best. So here, we feed the same timestamp that the decoder is going to predict. So you kind of like shift by one your encoder. So that means you kind of cheat because your latent variable at this point, it has information about this message, right? And that means if your language model can decode this information, it should get very good loss. It should, if it can decode it perfectly, then it should get like 0 loss, right? And in fact, it actually like gets very low loss. That means it's just like your representations that you learn, they carry a lot of information. Okay, so that's good. So we trained this language model, but now the problem is how you're going to use this during inference, because during inference, you don't get to see the future message. And for that, we train kind of like predictor model. So now essentially this model is fixed, the decoder, but it expects the kind of like right cluster. But we unfortunately don't know the distribution where this cluster was sampled from, and we have to kind of like reconstruct this distribution. So it's, I guess, similar to variational autoencoder a little bit. So essentially, you kind of like, you know what latent variable should be there, but you don't know how to choose it. And instead, what you can do, you can just to train this model, you can minimize the KL divergence between this distribution that your encoder predicts and the distribution that language model expects, so it can fit. It usually, obviously, it's not going to predict. It doesn't work as well as this one because you kind of like have to predict the future. It works, it gets higher loss, but it still works fine because when you actually use it, it can predict, it can generate nice dialogues. But later on, we're still going to change this distribution, so it's fine. Okay, so now we're going to talk about the results. So we're going to compare these 4 models. So RNN model is the baseline that I was talking about. The hierarchical model is just 2 layers of LSTM, so not very interesting. Baseline clusters, that's the clusters that we learn without EM. So that's basically the first approach that I described. And full model, that's our model. So first of all, let's look at the representations that our clusters see. So here on that side, we have 5 different clusters. So I basically took like 5 random clusters. I took representation for each of them, and I feed it to a language model and generated 1 sentence. And if you look at those sentences, they actually, even though they're different, they explain the same thing. So that actually means that our clusters represent the meaning, which is what we wanted to get. So for example, I guess let's see, this is generated for this input. So 2 books, 1 hat, and 2 balls. So for example, here, I would like the hat in 1 book. And here it says, I cannot give up the hat, so it wants the hat, but I can offer you the book and 2 balls. So that leaves us with 1 book and 1 hat. That's exactly what the first sentence says. So that's good. So that basically means we separated meaning and the kind of representation of that meaning. We kind of like, that's the perplexity that we get on the data set, right? So we get slightly better perplexity than baseline model, but it's like not very significant. Then we just use this model for self-play. So basically like take one of this model and put it into self-play with baseline model, and then we put it to self-play with hierarchical model. And our model outperforms each of the model very good, so it can achieve the higher score. So that basically means because of this diversity that we get, because we can sample different meanings, we can get higher performance. Yeah. Yes. So basically, the way it works, we actually have 3 models. So 1 model where we learn representations, then another model where we have conditional model, conditional language model, and then 3rd model is actually the prediction model where we learn distribution over discrete latent variables. And then what we do, we take prediction model and conditional language model and feed them together, and that's going to be the dialogue model. So yeah, they're pre-trained, and self-play is just, we don't tune parameters. We just, the models are fixed and they just like play. So we're going to use reinforcement learning later, where we actually change parameters during self-play. So this was just, yeah, just to score. Okay, so now we can use actually, because of this structure, we can use reinforcement learning way more efficiently. So if you think about it, this model is only responsible for generating language. So what we need to do to get better strategy is actually choose what Z's we're going to give the model. So that means what we can do, we can fix this model. We don't change parameters for it. And we're only going to shape distribution over Z's for this encoder model. That basically means our language is going to stay constant. It's not going to diverge as we see in the previous, for the baseline model, because the model knows about each cluster, and you're just like maybe going to give it different Z, which is going to affect the meaning, but it's not going to affect the language. And that's actually a very important graph. So our model it's kind of like maybe a little bit hard to understand what it means. So, but essentially, this is trade-off of perplexity and reward. So if we get our previous, this is baseline model, right? So what happens is just, it can get very high reward, like 7.5, but what happens is just perplexity decreases. That means language becomes garbage. So even though it can achieve higher, that actually was the problem that I mean. It's just, when I said at the beginning, it's just like model can kind of cheat. They can just like communicate. They can agree to the good deals, but they can output the garbage because they don't care about the language. But in our case, we can get very good performance with very low perplexity. That's basically just like original perplexity that we have. So that's where we start at 5.4, and then we can just like get to 5.6 without kind of like decreasing perplexity. So this gap, that's the main result. So this is kind of like doesn't really matter because this is already a very high perplexity and it's not useful. But this part is very important. So that basically means it's just we can get much higher reward with much better language quality. And then, because now we can separate, we know the meaning, we can also improve rollouts. So that was baseline rollout where we just like sampled the sentences and it's not very good. But what we can do now, we can sample Z's, right? And because each Z is separated, it's kind of like different. So that means you get more diversity. You can explore space much better. And that's why you can get these diverse results. So here, you just like completely different sentences, and then you keep going. And this is 2, and then you get different points. So now what you can do, you can take like, for example, average, or you can just, so essentially this dialogue is much better. So you continue, you take this sentence and you keep going. So it also improves rollouts significantly. So yeah, now, so what we have, the results, baseline rollouts, that's also self-play without no rollouts. So it basically just like destroys the model with no rollouts. It gets like 9, 8.4, 10 is maximum score. And then also kills very easily baseline rollouts. So I guess this was fine to just like when we do self-play, but we also tried it to kind of like play against human. So we essentially took all of these models and just randomly sampled the model and got a human to chat with it. And we essentially asked human later to evaluate how human-like was the dialogue. So this was maximum was 5. So human playing against human can get 3.5 or 3.8, and human against human gets like 6.6 score. So our model with rollout can get much higher score. Oh, like not much higher, but like, I guess almost 1 point. And the language actually is also pretty reasonable. So yeah. And that's one of the sample of the dialogue. You can see that's 2 model, basically diverse rollout model is playing against the baseline model. Yeah, obviously not the dialogue as good as, so this was kind of like cherry picked, but I didn't spend much time, so it was many of those, I saw many dialogues like this. It was kind of good. Yeah, and there is some ablation study, so we kind of see that our model will generate fewer generic messages. I guess generic messages means like, it says like, oh, fine, I'm done, it's good, or like great. So it's getting like more creative. It tries to kind of like negotiate a little bit harder. So yeah, so also we observed way more messages that were not in the original data set, because I guess baseline model is just like usually copies whatever it has in the data set, but this one is more creative. Yeah, there was no repetition. I guess sometimes baseline model can, especially if you do reinforcement learning, it can like oscillate in one point and it keep continue the same deal. So that wasn't the case with new model. Yeah, so I guess basically like conclusion is we kind of like try to apply reinforcement learning. We kind of like essentially what we did, we decreased action space. Instead of using words, we decreased it into some, I guess you can think of this as each action now is intent, or like, and basically how your action is going to affect the entire dialogue. Instead of, for baseline model, your policy is just like producing next word. So we kind of like reduce our model to using these intents, and then because of that, now you can, using reinforcement learning, you can choose these intents and do much better. And yeah, obviously, I guess we tried it only on one data set. I guess we tried to use it on a different data set, but we haven't finished it yet. But yeah, I guess in the future, maybe if somebody is interested in this approach, we can try to scale it to much larger domains. So the idea seems like pretty generic, so might work. Yeah, so basically I described today 2 papers. This is mostly describes the dataset and baseline model, and that's the ICML paper that I'm going to present next week about this discrete latent variables. So we also have some open source code for the first paper. So it has dataset and it has the model. So if somebody is interested, you can just go ahead and try it. And yeah, yeah, that's it. If you have any questions, feel free to ask me. Mm-hmm.
Any links to papers or something you can share?
Yeah, papers on archive. So that's the links. Yeah, I should have put like QR codes or something. Yeah, I guess if anybody comes going to ICML, I'm gonna poster and talk is gonna be on Friday.
Can it be generalized? I mean, can it be used with more unseen types of items? For example, not just like beds and books and but cars and.
Yeah, I guess. I mean, in this particular model, it cannot generalize because it's actually like encoder that we have that encodes an action distribution that we predict is actually very restricted to the, because essentially we generate distributions of max distribution over all possible, and if you add like some new items, it doesn't know it. But yeah, that's actually interesting thing. Yeah, I guess that's, maybe it can be done something, but I'm not sure. But yeah, this particular model cannot do this.
Any other questions?
Do you have some ideas how to extend?
Mm-hmm.
To continue my previous question, do you have any ideas how to extend your model to have more freedom with items, with objects?
Yeah, so let's see. So yeah, I guess now question is basically, you have to now sort of generate the, it's kind of like now you get into generative model a little bit, I think, because this model is sort of like discriminative because it knows all possible actions, but now you have to, there could be something that you haven't seen. So yeah, from top of my head, I'm not sure. I have to think about it.
Can you make a little bit clear? You have said in the middle of your talk that you used like tree search, but it's not clear how it is related, because afterwards you showed the model where you use latent variable to decode like words and predict current action. So where is?
Yeah, so tree search only used this is rollouts, right? So we only use tree search on the fixed model. So we use tree search for training. It's only on inference part. So essentially you'll have already pre-trained model. So what you do instead of just like, it's kind of like beam search, right? So in beam search.
So you use it for training or
for inference only?
For inference.
Yeah. Essentially what you do is just, if you don't use rollouts, you kind of like predict one sentence and you go with that.
Yes.
So what you can do instead, you can predict multiple sentences, kind of like roll it out, and then do it until the dialogue ends, and then pick the one that gives you higher score and just one sentence, kind of like the beginning of rollout, and then you continue.
And so you perform these for separately for one party and for another party?
Yeah. So that's very, I guess, more expensive because, but that's only inference.
And also, it's limited on number of objects. So because in different dialogues, instances of dialogues, there would be different number of combinations that we can.
Yeah. This I guess also number of like basic objects, they kind of like encoded on the text, right? Because human, when they generated these dialogues, they only saw the object, right? So if you want to add like some new objects, basically you're not gonna see corresponding word for this object, right? So it's kind of very constrained, I would say. So the dialogues in the data set, they only know that you have these objects, not anything else.
Can you comment how it can be extended or used for the task-oriented dialogue, such as like booking flights or hotels or?
Yeah. So I guess this approach in the second paper, I think it's kind of like essentially what it does. It helps you to kind of like unsupervisedly understand, because you're using clustering, unsupervisedly understand what could be some possible like outcomes of the dialogue, right? So I guess in task-oriented dialogue, you kind of you can do task, but then maybe you can do it like in different ways, but you also don't know like some intermediate state of the dialogue. I guess maybe it's not clear. So essentially, what it helps you. It's kind of like, let me see how to explain. So the outcomes may be limited, the number of outcomes, the way how you can finish the task, it's fixed, right? So even for booking, it's basically, you can discretize.
All slots should be filled.
Yeah, right. But then what can happen is just at the beginning of the, like in the middle of dialogue, there could be, maybe different permutations of like how you put something after another, or right? Yeah.
Yeah, it's about the sequence, how you fill slots.
Yeah, essentially the problem. So what we can do is generic. So there is no models right now that can. We can either like generate sequences, right, which RNN, but we cannot generate distribution over all permutations because it's just unbounded, right? So how you can do that? Because one way to do that is just like kind of like reduce the action space. Essentially, some of the permutations may be kind of like similar, so that's why one part of them going to represent maybe a prefix of some permutations, one discrete variable, and that's kind of like hybrid between the sequence generation and just, so it's, I guess the analogy I have is just, you have three types. You have like greedy generation, that's sequence. Then what you can do, you can just do brute force, where you can try all permutations, but something in between, I guess usually it's dynamic programming, right? So you kind of like, you still do some kind of like brute force, but you discretize your state. So I think this idea goes towards like something in between greedy and brute force. And
so have you tried another representations for this Z vector? So now you use all possible permutations of your items, yes?
Mm-hmm. Yeah.
But like what you have said, like in Atari game, when you have just actions, so maybe you can try this factorized representation where you have like, say, balls 5 or books 3.
Yeah.
So you should not encode all the possible outcomes
Yeah.
in the vector. Have you tried these?
I haven't tried, but yeah, essentially, I guess this is kind of like similar. So in, for example, I guess in Atari is simpler game, but like in harder games, StarCraft maybe, they usually use hierarchical reinforcement learning. So that's, you have like master policy and then you have sub policies. So essentially sub policy is kind of like one skill. Essentially maybe sub policy is just take units and build or like attack opponent, right? But now this sub policy knows that it should select each unit, it should send it to the right. But the problem with this approach is just like, how do you learn these sub policies? Because this is unsupervised, right? Essentially, because if you don't supervise these sub policies, just like the model is not gonna learn like what its sub policy should represent, right? So how does it know? It's just like this sub policy should like be responsible for attacking or like gathering resources, something like that. Essentially, I guess the way I've represented it in my head is just you have this tree of all possible actions, but then what you do is hierarchical reinforcement learning, you kind of like connect some of the actions in between. So, and that's, I guess, kind of like similar to the, but yeah, I haven't tried for this particular problem. I'm actually like, I'm working on the current, my project is, it's actually not continuation of this, but it's very similar. So I wanted to use natural language to supervise reinforcement learning. So I have a game, RTS game, which is slightly, it's simpler than StarCraft, but it's also very complex. So if you just apply reinforcement learning to it, it's not going to learn anything. So the way I wanted to do it is just, I'm going to have humans to kind of like give instructions. So instruction in natural language instruction could be take this unit, go to the top of your map and build like barrack, right? So what model have to do, it should take this language, understand it, and like click through actions. So that's very complicated. But essentially, it's still more information than if you just like gonna give rewards, like if you win the game or not, right? It's just like action space is too huge. But now you kind of like, because you have this language, you can have kind of like some suggestions. So you can connect you can select trajectories that close to the instructions.
Do you use maze base for these?
No, we actually build the RTS game. Oh no.
So why don't you use this the same stuff you have was developed?
Yeah, so we want to use maze base, but we realized that that's probably not very complicated environment. So we decided to build much.
But you can extend it or not?
So there's already been work. I guess last ICML there was kind of like this. Also like either maze based, so you basically like telling, I guess in the maze it works, for example, in the maze you have doors and you have keys, right? And you need to pick particular key to open the door. So, and that's actually like hierarchical reinforcement learning. So one policy needs to represent basically which key you need to pick. So, but that's already been done. So that's kind of cool, but it's not as complicated. While in RTS game, you can do a lot of stuff. There is so many strategies you can do, so it's very complex. And it's kind of like also more fun. I've been playing myself for a lot of times. We're gonna soon open source this game. So.
Okay, thank you. Any other questions? So let's thank our speakers.